So maybe are you ready to start?
I'm ready to start. Yeah.
Okay, good. Then let's start. So welcome everyone. Today we're very happy to have Jason Lowe from California State University, Northridge. And he's going to be talking about stability of the cotangent bundle on some surfaces. So please go ahead.
Okay, thank you. Yeah, thanks to Pedro for the invitation to speak at this seminar. So the outline of the talk today is as follows. So I was told that there's a 30-minute portion in the start and then plus a 60-minute portion that follows. So for the 30-minute portion, I'll try to give an introduction to the idea of stability. So that includes Mumford-Takemoto stability or slope stability, and also the idea of bridgeline stability. So I won't give a full definition of bridgeline stability, but I'll try to give an idea of how to think about it. And then for the remaining part of the talk, I will try to give a motivation for the problems we are thinking about. And then I'll try to describe some of the results that we have on K3 and general type surfaces. And hopefully we'll have time to talk about some results on final surfaces as well. And is the writing big enough on the screen?
For me, it is, yeah.
Okay, yeah.
A bit larger? So is it possible to do it a bit larger?
Yeah, I can try to, if I do this and try to write a bit bigger. Yeah, okay. Hopefully that'll, yeah. All right, so, yeah. So for Mumford-Takemoto,
yeah, I think you could write slightly bigger, I think. Slightly bigger.
Okay. Okay. Let me try.
Some people are sitting more far away.
Oh, I actually forgot how to change the size of like the line. Where is it? Not here. Oh, here, I think. Oh, maybe bigger like that. Okay. Is it better like this?
Yeah, I think it's better.
Okay. Yeah, so for Mumford-Takemoto stability or slope stability, here's the idea. So in algebraic geometry, we care a lot about moduli spaces. And when it comes to moduli spaces, we want moduli spaces to be nice. So this includes, by nice, we often mean we want the moduli space to be of finite type. So it's finite dimensional. And maybe we want the moduli space to be, say, proper. So it will be compact as a topological space. And in order to get these nice properties, a lot of the time we have to impose a stability condition on the geometric objects that we are trying to parameterize. So this is a motivation to use some kind of stability on the objects we are looking at. So let's say X is an arbitrary smooth projective variety over the complex numbers of dimension n. And let's fix an ample class on this variety. Then for those of us who work on moduli spaces of sheaves or complexes of sheaves, we can define a number for any non-zero coherent sheaf on X. So for any non-zero coherent sheaf or for any non-zero object in this abelian category of coherent sheaves on X, we can define a number. So we'll denote it by mu sub omega. Omega is the ample class we are fixing. So this is a number coming from our coherent sheaf E. And we define it to be the intersection number omega to be n minus 1 times the first Chern class of E. So this would be a number divided by the CH0 or the rank of this coherent sheaf. And so sometimes we call this number in the numerator the degree of the coherent sheaf with respect to this ample class we are fixing. And CH0, sometimes we write it as RK for rank. And if the coherent sheaf happens to be a sheaf with rank 0, then we just define this number to be positive infinity. So we define this to be positive infinity if the rank equals 0. And using, so for every non-zero coherent sheaf, we get such a number mu. And this allows us to define slope stability or Mumford-Takemoto stability. So we say a non-zero coherent sheaf E on X is slope semi-stable or mu semi-stable if for every subsheaf, let's say F of E, such that the rank of this subsheaf is strictly between 0 and the rank of E. We have this inequality. So the number, the mu or the slope of F is less than or equal to the number or the slope of E. Yeah, so very roughly, a coherent sheaf is mu semi-stable or slope semi-stable if every subsheaf has a mu that's equal to or smaller than the mu of E itself. And if you find that every time you check this inequality, you actually get a strict inequality. If that always happens, then we say the sheaf is slope or mu stable. So if you always get a strict inequality here, then we say the sheaf E is mu stable. And you can, from the definition of mu and the definition of slope stability, yeah, you can easily check that if you have a semi-stable sheaf with rank equal to with positive rank, then it has to be torsion-free. And so if you get bored at some point, this is a little lemma that you can try to prove. And here are some examples or / exercises that are related that you can think about if you like, if you haven't seen this sort of things before. So every rank 1 torsion-free sheaf is slope stable. So every rank 1 torsion-free sheaf is mu stable. Yeah, for any ample divisor omega. And then another lemma or proposition on semi-stable sheaves or constructing semi-stable sheaves is as follows. So suppose we have 2 semi-stable sheaves. So suppose E1 and E2 are mu semi-stable torsion-free sheaves of the same slope. Yeah, and here by the word slope of a sheaf, I mean its number mu with respect to the omega we are fixing. So if I take 2 torsion-free slope semi-stable sheaves with the same slope mu, I can try to form an extension of these 2 sheaves. And I don't really care whether the extension is trivial or not. So then any extension, and let's call this extension E, any extension of these two sheaves, E1 and E2, is slope semi-stable as well. So this is one way to get a new semi-stable sheaf. If you already have two existing semi-stable sheaves with the same slope. And so here's an outline of a proof of this statement. So, okay, if we want to check that this extension is slope semi-stable, then according to the definition of slope stability, we have to take an arbitrary subsheaf with this condition on its rank. And then we have to check that the slope of the subsheaf is less than or equal to the slope of this sheaf E that we're hoping to be semi-stable. So let's take any subsheaf F of E with rank strictly between 0 and the rank of E. And so we want to say something about F based on what we know about E. And what we know about E is that it's an extension of E1 and E2. So E fits between such a show exact sequence of sheaves, and F is a subsheaf. So if we think of this as a diagram in the category of coherent sheaves, we have an inclusion. And then this show exact sequence would induce a show exact sequence with F in the middle. So let's say the induced sub is, let me just use a normal arrow. This is the induced sub, which injects into E1. And let's say F double prime is the induced quotient of F, which injects into E2. So the upper row in this diagram is induced from the lower row. And then we can say, well, now F prime is or isomorphic to a subsheaf of E1. F double prime is isomorphic to a subsheaf of E2. And we are assuming that E1 and E2 are slope semi-stable. So we can say something about the slopes of F prime and F double prime. So by the slope, so I'll probably start omitting the subscript omega from now on. So by the slope semi-stability, and I'll write double S for semi-stable. Yeah, double S for semi-stable. By the slope semi-stability of E1 and E2, we know that the slope of F prime is less than or equal to the slope of E1. And the slope of F double prime is less than or equal to the slope of E2. And then what we want is for the slope of F to be less than or equal to the slope of E. And now you can try to prove this algebraically just by looking at the writing out the definitions of all these mu's and trying to manipulate the terms. But I want to explain why this is true in a different way by drawing some pictures. So this is an aside that explains a somewhat different way of thinking about the slope of a coherent sheaf and the idea of slope stability. So for before, in the definition of slope stability, we define this number mu for any non-zero coherent sheaf. And now I'm going to define a somewhat different, number for a non-zero coherent sheaf that actually plays the same role, even though it looks different. So if we take any non-zero coherent sheaf on X, let's define a different number, which we'll call phi. This is going to be a number between 0 and 1. 0 and 1. And So how do I get this number 5? Well, I first consider this complex number, Z of A, which I'll define to be, so I'll calculate the degree of this coherent sheaf, take its negative, and I'll let it be the real part of my complex number. And then for the imaginary part, I will take, I'll just use the rank of this coherent sheaf. And then I can look at where this complex number is on the complex plane. So since A is a coherent sheaf, the rank is always bigger than or equal to 0. So I know this complex number is always in the non-strict upper half plane. And then when the coherent sheaf A has rank equal to 0, so when we have a torsion coherent sheaf, we know the degree is non-negative. So if the rank is 0, which means we lie on the real axis, then since the degree is non-negative, this complex number has to lie at either the origin or the negative real axis. So this complex number Z of A can only appear either at the origin, at the here's the highlighter. Yeah, at the origin, the negative real axis, or the strict up half plane. Yeah, and so let's suppose, this complex number is maybe in the strict upper half plane, just out of simplicity. Then we can measure this angle, the face, and then now this angle is going to be some number between 0 and pi. Let's normalize it by dividing it by pi. And what we get by dividing by pi, we'll call that number phi of A. So phi of A would be between 0 and 1. And then you can check that if you use the same, if you look at the definition of slope stability, but every time you see mu sub omega, you replace by this number phi, you'll see that you get an equivalent definition of slope stability. And that comes from the fact that if you have two coherent sheaves, then the phi of one sheaf A is less than or equal to the phi of another sheaf A prime, if and only if you have the same ordering on their slopes. So this means that when it comes to defining the slope stability of a coherent sheaf, we can use this number phi instead. And now the reason why I wanted to talk about this number phi and the complex number Z is when we think about this complex number, this function Z is additive on show exact sequences. So an interesting property of this Z is in any show exact sequence of coherent sheaves. So let's say from 0 to A1 to A to A2 to 0. Z of the middle term A is Z of the term on the left plus Z of the term on the right. So this is just because the chain components are additive, show exact sequences. Now let's think about this equation in terms of where these numbers are on the complex plane as well. So here's the complex plane again. So let's say maybe Z of A1 is here. Z of A2 is here. So we can draw these line segments from the origin. So then phi of A1 would be this angle divided by pi. Phi of A2 would be this angle divided by pi. And now the to get the angle of A, or phi of A, we can look at where this number is on the complex plane. But this number we can think of as just the sum of this vector and this vector. So geometrically, we draw a parallelogram using these two vectors. And then this new vertex is where z of a is. And this angle would be phi of a times pi. So geometrically, this is how you get the phi of an extension using the phis of the two sheaves that are used in the extension. And so now, if we come back to this thing that we wanted to prove, then this is what's happening. So, so f is an extension of f prime and f double prime. E is an extension of E1 and E2. We know the mu of f prime is less than or equal to the mu of E1. So equivalently, phi of f prime is less than or equal to phi of E1. We also know phi of f double prime is less than or equal to phi of E2. And we want to show phi of f is less than or equal to phi of E. So let me draw everything in a picture. So okay, here's another copy of the complex plane. So let's say maybe z of E1 is here, and z of E2 is here. So here are the line segments connecting them to the origin. So z of E, which is the sum of these two vectors, z of E would be, let's say, so I need to add these two vectors geometrically. So let's say it's this plus this. So here's z of E. Now, let me also try to draw z of f prime and z of f double prime. Now, by our assumptions, the angle for f prime should be less than or equal to the angle for E1. So let me try to draw, let's say, f prime here, because it's supposed to have a small angle than E1. And then the angle, the phi of f double prime, is supposed to be less than that of E2. So maybe I should draw, let's say, z of f double prime here. And now I need to add these two vectors. So let's say here's their sum. So this would be z of f. Yeah, so the idea is when you go from E to f, what happens is the angle of when you go from E to f, it's as if you're replacing E1 with f prime, and you're replacing E2 with f double prime. But then when you switch from E1 to f prime, the angle reduces. And when you switch from E2 to f double prime, the angle also decreases. And so this new vertex you get from these parallelograms, this new vertex is going to move in such a way that its angle from the real positive real axis decreases. And that's why the angle of E will be bigger than or equal to the angle of f, which is what we want in order to show E is slope semi-stable. So yeah, so anytime you have two slope semi-stable sheaves of the same slope, any extension is also slope semi-stable. And this is a way to build new semi-stable sheaves out of existing ones. So these are some ideas surrounding slope stability. Yeah, maybe I'll pause here for a second to see if there are any questions. Okay, should I continue?
No questions, I guess. Yeah.
Okay.
Thanks.
Yeah. And Okay, so all of these so far is about slope stability. Now, how do we think about bridgeline stability? So let's review slope stability for a second before we move on. So to define slope stability, well, slope stability is defined for coherent sheets. So slope stability is defined for objects in the abelian category of coherent sheets. And the way you determine whether an object in this abelian category is semi-stable or not is you look at sub-objects, or equivalently, you look at a show exact sequence with your object in the middle, and then you try to see whether there's an inequality of the numbers mu's. And so for bridgeline stability, the idea is as follows. When it comes to bridgeline stability conditions, so this is an informal way to think about bridgeline stability. Instead of thinking about just objects in the category of coherent sheets, you would think about objects within what we call the heart of a T structure. So let's call it A. And this would be, so let me write a bit more. So you will replace the category of coherent sheets with the heart of a T structure in the bounded derived category of coherent sheets. Now, the important thing here is that this heart of T structure, let's call it A, this is an abelian category. Yeah, so you can talk about kernels, co-kernels, and show exact sequences in this category. And then instead of using this formula for Z, which you can use to define a number phi, you will use a different formula. So you replace the Z from above for slope stability with a Z with a different formula, but it has to be a group homomorphism. Let's still call it Z from the Grothendieck group of the derived category to the complex numbers. So here we are thinking of C as a group under addition, with the requirement that every non-zero object in this abelian category has to be mapped into the upper half plane. And by the upper half plane, I mean, it doesn't include the origin. It includes the negative real axis and also the strict upper half plane. Yeah, so once you have all this data, you can define a number phi for any non-zero object in this abelian category. Yeah, and then you would say an object is bridgeline semi-stable if for every sub-object, the phi of the sub-object is smaller than or equal to the phi of this object A itself. So then you get a notion of bridgeline stability or bridgeline semi-stability. But for the sake of concreteness, let me just write down a bit more. So more concretely, so an object that's non-zero and in this abelian category or in this heart of T structure is called bridgeline semi-stable. And let me use sigma to denote all these data defining this bridgeline stability. So sigma here refers to a bridgeline stability with the data above. So we say a non-zero object A in this abelian category is bridgeline semi-stable. If for every short exact sequence in this abelian category with A in the middle, let's say from 0 to A prime to A double prime, where A prime and A double prime are non-zero, we have that the number, the phi of A prime is less than or equal to the number phi of A. And we say this object is bridgeline stable if we always get a strict inequality. So this is one way to think about a bridgeline stability condition. Okay. So if it's okay, I'll write down some examples of bridgeline stability conditions on surfaces and move on to the next part of the talk. Okay. So here are some concrete examples of bridgeline stability conditions on surfaces. So I'll write down a concrete abelian category. I'll write down a concrete formula for this complex number Z. Yeah, so you will know how to define concretely the phi for every non-zero object in this abelian category. And so you have a very concrete definition of what it means for an object to be bridgeline semi-stable. So from now on until the end of the talk, X would be a smooth projective surface. And so to define the abelian category that goes into a bridgeline stability condition on a surface, I have to mention the idea of the Hardaner-Singhan filtration for a coherent sheaf. So every time you have a non-zero coherent sheaf on a smooth projective variety, and if you fix an ample class omega on your variety, what you get is a filtration of this coherent sheaf. So we get a harder Narasimhan or HN filtration. So I'll write it as E node contained in E1 all the way to say En, which is E itself. And let's say E node is 0. And this is a filtration in the category of coherent sheaves. So a filtration for sheaves. So every non-zero coherent sheaf has a filtration satisfying these properties. So the first property is every factor in this filtration, so E1 mod E naught, E2 mod E1, and so on. Every single factor EI mod EI minus 1 is slope semi-stable. Yeah, and the second property of such a filtration is if you look at all these factors in order from left to right, then their slopes, their mu's, are strictly decreasing. So the slope of E1 mod E naught is bigger than the slope of E2 mod E1, and so on, all the way to the last factor in this filtration. Okay, so now we can define concrete bridgeline stabilities on surfaces. So this description of HN filtrations works for any smooth projective variety. Yeah, but for now on, let's say X is a surface and omega is an endpoint class on X. So X is a surface. And in addition to omega, we can actually pick another divisor on X as well. So here, let's say omega and B are divisors on X, but we require that omega is endpoint. Then here's an abelian category you can use to form a Bridgeline stability condition. So this abelian category is defined using both omega and B. So I'll use subscripts omega and B. So this is the category of all the objects in the boundary derived category of coherent sheaves. So all the complexes of coherent sheaves such that the cohomology at degree -1 has all its Hardaner-Singhan factors with slopes less than or equal to 0. So in other words, we require that the cohomology at degree -1 of this complex, when you look at its HN filtration, all the factors have to have slopes or mu's less than or equal to 0. And then for the degree 0 cohomology, we require that all the Hardaner-Singhan factors have slopes strictly bigger than 0. And then we want all the other cohomologies to vanish. So the cohomology has to be 0 for every time the degree where you're taking the cohomology is not equal to 0 or -1. Yeah, and you can show that this subcategory of the boundary derived category of coherent sheaves is an abelian category. And now, what about the group homomorphism C? Well, it's also defined using omega and B. So for these, let me pick an object E. So for this group homomorphism, the definition is negative the integral of e to the minus b plus I times omega times the Chern character of E. And if you compute this number, it comes out to be minus the second twisted Chern character of E plus omega squared over 2 times the twisted Chern 0 of E plus I times omega times the twisted Chern 1 of E. And what I mean by this twisted Chern characters is as follows. So the twisted Chern character CHB of E is just e to the minus b times the Chern character of E itself. And if we write this out according to like the different degrees in the child ring, we will call the degree 0 part the CH0 upper B of E. And the degree 1 part is called CH1B of E, and so on. Yeah, so this is what I mean by these twisted Chern characters. And so using this abelian category and this group homomorphism, you can define a number phi for every non-zero object in here. And so you can talk about what it means for a non-zero object in this abelian category to be Bridgeline semi-stable or stable. And so let me, for the sake of completeness, let me state it as a theorem. So we think this is often attributed to Alcara, Bertrand, and also Bridgeline. So as in, so Bridgeline first write down almost this definition of stability conditions on K-free surfaces, but then Alcara, Bertrand noticed that if you use this version, then it works on any smooth projective surface. So the statement is, if you take this pair this pair consisting of the data of this abelian category and this group homomorphism, and this forms a stability condition, or a Birchland stability condition on this arbitrary smooth projective surface X. And just to emphasize, let me draw this picture again. So for any non-zero object in the abelian category, you can think about this complex number on the complex plane. You can look at its angle from the positive real axis divided by pi. So you get this number A, phi of A. And then you can use this number phi to define Birchland semistability or sigma semistability of A itself. Okay. So so in the title of the talk, right, there's this word stability. So far we've been talking about slope stability. It's used in the definition of Birchland stability conditions. So the word stability in the title of the talk refers more to Birchland stability. So we care about the stability of the cotangent bundle, or actually the stability of the tangent bundle on some surfaces. And this is a reason why we care about the Birchland stability of the cotangent or the tangent bundle. So this is the motivation for the next part of the talk. So a motivation is this theorem from the 80s. So by Donaldson and also Uhlenbeck Yau. Oh, and yeah, I should mention that, right, the rest of the talk is in progress and also joint work with Tristan Collins, Yun Shi, Shi Yun, and Xintong Yao. Okay. So in the 80s, there was this theorem by Donaldson and Uhlenbeck Yau that says if you take a compact Kähler manifold and you take a vector bundle E that's irreducible and holomorphic on X, then there are two things that are equivalent. So one is the fact that that this holomorphic vector bundle E that meets a metric solving the Hermitian Young-Mills equation, or the HYM equation. So this equation is a differential equation that you can write down using this vector bundle E. So it's a question in analysis or differential geometry, if you like. Now, this statement is equivalent to a statement in algebraic geometry. So on the algebraic geometry side, we can think about E as an algebraic vector bundle, and we can ask the question: is it Mumford-Takamoto, or is it a slope stable? And these two statements turn out to be equivalent. But that was in the 80s. And since then, on the equation side, there've been the theory of Hermitian Young-Mills equation has evolved into theories of deformed Hermitian-Young-Mills equation, or DHYM equation. And on the algebraic geometry side, as we know, now we have bridgeline stability conditions and other types of stability conditions that we can put on the derived category. So a few years ago, Collins and Yao asked this question. So on the equation side, so if we still take a vector bundle on a compact Kähler manifold, but for us, we can just think of X as a smooth projective variety. So if you take a smooth projective variety, on the equation side, you can ask whether a vector bundle E on X that meets a solution to the deformed Hermitian-Young-Mills equation. So D here is denotes deformed. And then on the algebraic side, we can ask whether this vector bundle E is bridgeline stable. Yeah, so the question is, what's the relation between these two statements? And there are some results on when E is a line bundle. So results on line bundles. So the result by Jacob Su. And in algebraic geometry, the first result, I think, was by Collins and Shi for P2 blown up at a point. And later, together with Collins, Shi, and Yao, we also obtained some results on elliptic surfaces. But these are results for line bundles. So when E has rank 1, and much less is known for higher rank bundles. So my impression is, my understanding is, one difficulty for higher rank bundles is it may not be as easy to define the deformed Hermitian-Young-Mills equation when E is a bundle of higher rank. Yeah, but then for us algebraic geometers, the question is very concrete when E is a higher rank bundle. We have examples of bridgeline stabilities on any smooth projective surface and some smooth projective threefolds. And we can ask the question, if we take a high rank bundle on such a variety, is it bridgeline stable or not? So, so this side of the picture has a very concrete question that we can try to answer for higher rank bundles. And the reason why we focus on the tangent bundle or the cotangent bundle in this talk is there are a bit more results on the equation side for the tangent or cotangent bundle on surfaces. So the focus today is on the tangent bundle or the cotangent bundle on surfaces. Because on the equation side, a bit more is, even though not very much is known, at least a bit more is known for this particular higher rank bundles. Okay.
So, Jason, can I ask about the question?
Of course, yeah.
So does it mean that for every kind of deformed Hermitian-Young-Mills equation, you have a particular bridgeline stability condition for which the equivalence holds, or is there one which works for all of them, or one?
So for the data that goes into the bridgeline stability condition, only yeah, for us it only depends on the ample class omega that we are choosing.
So this is the fixed one. Okay.
Yeah.
Okay, thanks.
Oh, sure. Yeah, okay. So here are some of what we know on K3 and genotype surfaces. In the case of K-free surfaces, the situation is quite simple, thanks to a result by Huybrechts. So we have a proposition. So take any K-free surface X, then the cotangent bundle omega is Bridgeline stable. So here's our notation for Bridgeline stability. Omega here is any M-pole class on X. And if you remember the second part of the subscript, it's another divisor B, but for us, we always choose that divisor B to be 0. Yeah, so the cotangent bundle is always stable with respect to such a Bridgeline stability. And here omega is arbitrary for any M-pole class omega on X. And so this is a quick corollary of a result by Huybrechts, where he classifies the minimal objects in this abelian category that we use in the definition of Bridgeline stability conditions. So this is for K3. Okay, so now for genotype surfaces, this is this is the start of the story for genotype surfaces. We have this theorem by Aubin Yao from the 70s that says if you have a smooth projective variety where the canonical class is ample, then the cotangent bundle is always slope semi-stable with respect to this canonical class. And if you know that the cotangent bundle is non-split, so if it's not the direct sum of two line bundles, so if the cotangent bundle is non-split, then we actually know that it's slope stable with respect to the canonical class. And this is useful for us in terms of talking about the Bridgeline stability of the cotangent bundle, because if we know that the cotangent bundle is slope stable, it has a better chance of being Bridgeline stable when we use the canonical class as our omega in the definition of Bridgeline stability. And so because of this result, we are motivated to consider surfaces where the canonical class is ample, and hence that brings us to surfaces of genotype. And okay, so let me say a bit more about how to go from the cotangent bundle being slope stable to Bridgeline stable or Bridgeline semi-stable. So if we already know that the cotangent bundle is slope stable, let's say with respect to some ample class omega, then we can check that it's what we call twisted Giesecke semi-stable. So sort of Giesecke semi-stable by using a twisted version of the Hilbert polynomial. And if we know that a coherent sheaf is twisted Giesecke semi-stable, then we can prove. There's a result with Martinez, Christian Martinez, that says, so then there is a positive real number T naught such that every time T is bigger than T naught, your coherent sheaf, and in this case, the cotangent bundle is Bridgeline semi-stable. If you choose the ample class to be T times omega, yeah, and the omega here comes from the omega you use in determining determining the slope stability of your of the cotangent bundle. So let me draw a picture to visualize this. So this is saying if you already know the cotangent bundle is slope stable for some ample class omega, then you can think about this one parameter family of Bridgeline stability conditions. So you can visualize it as a ray. So we have this one parameter family of Bridgeline stability. So here I'm only writing TK because the path for the divisor B, that's equal to 0. So we can think of this one parameter family as a ray. So the result we have is, well, there's some point corresponding to T node. So there's some stability in this one parameter family, such that beyond this point, the cotangent bundle is always Bridgeline semi-stable. So for all the Bridgeline stabilities here, the cotangent bundle is Bridgeline semi-stable. But this cutoff point may not be optimal in the sense that from the theory of stability, there's actually a cutoff point that may be even lower. That's what we call a wall or mini wall in stability conditions, such that for every stability upwards from that point, we know the cotangent bundle is Bridgeline semi-stable. And then at least for a small part of the interval below this wall, we know the cotangent bundle is not Bridgeline semi-stable. So if you go just a little bit below this wall, say for epsilon, then we know the cotangent bundle is not Bridgeline semi-stable. And so our goal is to often to find an example of T node that's as close to this wall as possible. So as close to the wall, but above the wall as possible. So this is our goal when it comes to concrete computations. So how do we find an example of such a T node, and then how do we improve such an estimate or such an upper bound of this wall? So we need to write down some concrete stuff. So how to find and improve such an upper bound T node for this wall of Bridgeline stabilities. So here's a standard argument. So we assume that we start by assuming we are looking at a stability condition exactly on the wall. So suppose we have a Bridgeline stability that's exactly on or at the wall. And when you say this in the theory of stability, what it means is a bunch of things, one of which is there is a short exact sequence in this abelian category we defined earlier. So the ample class that goes in defining the abelian category is T times K. So here we are assuming the canonical class K of the surface is ample. And we are assuming the divisor B is 0. Since the divisor B is 0, we just omit that subscript. So saying you have a Bridgeline stability at the wall means inside this abelian category, there is a short exact sequence. with the cotangent bundle in the middle. So let's call the sub-object A and the quotient object Q, where the numbers phi's for all these objects are equal. So phi of A equals phi of the cotangent bundle equals phi of the quotient object with respect to this Bridgeline stability condition. So this show exact sequence, we often call it a destabilizing sequence. So I'll denote it by ds. And so to calculate and improve such a T-node, we often start by looking at a destabilizing sequence. And then we will try to find an upper bound for this parameter T. So we'll find an upper bound for T. Let's say T upper star. Yeah, this way, if we look at a stability condition where the parameter T is strictly bigger than this upper bound T star, then that means such a sequence cannot happen. And that would imply that the cotangent bundle is Bridgeline semi-stable. So then every time your parameter T is strictly bigger than this upper bound T star, you get the cotangent bundle is Bridgeline semi-stable. So this is one way to get a statement that says the cotangent bundle is Bridgeline semi-stable for particular Bridgeline stability conditions. Okay, so in terms of concrete computations, it comes down to analyzing these destabilizing sequences. And one of the properties of these sequences is that all the phi's of these objects are equal. And if you remember, these phi's depend on the complex number z omega b, which is defined in terms of the Chern characters of these objects. Yeah, so a lot of the time, finding this T-node comes down to looking at these show exact sequences and understanding the Chern characters and putting constraints on the Chern characters. And okay, so now if you look at such a show exact sequence in this abelian category, intuitively, maybe because the cotangent bundle is only of rank 2, we are tempted to think, well, maybe it's not so hard to analyze these sequences because the object in the middle has rank 2. But then remember, this is no longer the category of coherent sheaves. So even though A is a sub-object of a rank 2 object, the rank of A may actually be 2 or higher. Yeah, so these objects can actually be quite complicated. So in order to analyze these sequences, one thing we do is we often try to find constraints that force the rank of A to be small to begin with, so that these objects A and Q are easier to analyze. So a concrete problem when you try to understand these sequences is even though the rank of the cotangent bundle is 2, the rank of A may be high. So an idea is we want to force the rank of A to be low to begin with. And this is one way to force the rank of A to be low. So we have a proposition. So suppose A is this sub-object in a destabilizing sequence for the cotangent bundle. And let's write omega to denote T times K. So omega is the ample class that goes in the bridgeline stability condition that we'll be using. Then we can find an upper bound for the rank of A, given by omega times the first Chern class of the cotangent bundle over omega squared times D plus the square root of D squared plus 1. And here, what I mean, so D is a number. D is actually the bridgeline slope, which is the negative of the imaginary part of the complex number for the cotangent bundle divided by the real part of that complex number. And if you write down what these are in terms of using the definition of this group homomorphism we wrote down earlier, this number, capital D, is just the second Chern character of the cotangent bundle minus omega squared over omega times the first Chern class of the cotangent bundle. And if you write it down even more explicitly, you can write it as tau sub x over twice k squared, k being the canonical class, times 1 over t minus t. And we write it this way because this number tau seems to carry a special meaning. We know it carries a special meaning. So tau is defined to be k squared minus twice the second Chern class of the surface or of the tangent bundle. And this is a number that comes up a lot in all these calculations for stability conditions. But it also seems to play a role in the geography of surfaces of general type. So this number is significant, plays a role in calculation in stability conditions. And I think in some literature, this is called the index of the surface X. And the way it's related to the geography of surfaces of general type is as follows. So this picture will be familiar to some of you. So if we focus on minimal surfaces of general type, then we have this picture. So we can look at the second Chern class of the tangent bundle. We can also look at the self-intersection number of the canonical class. Yeah, and we know that these two numbers have to be they are integers, positive integers. So we put 1 on both x's. So both of these two numbers are at least 1. And by Noether's inequality, we know that if you plot the point C2 comma k squared, right, it has to be above this line, but it also has to be above a line given by Noether's inequality. So we draw like this. So that line is given by k squared equals 1 over 5 times C2 minus 36. So this comes from Noether's inequality. Yeah, so the inequality is k squared is bigger than or equal to this, but here I'm just drawing the boundary line. Yeah. And then there's also another constraint on the C2 and the k squared of a minimal surface of general type. So this order pair has to be below a line called the BMY line. So there's also the BMY line, k squared equals 3 times C2. So BMY as in Bogomolov, Miaoka, Yao. Yeah, so for minimal surfaces of general type, the order pair C2 comma k squared has to be in this region. And now, if you draw the line tau equals 0, so if you draw the line k squared equals 2 C2x, you'd be a line through the origin with slope equal to 2. So let's say it looks like, so 1, 2 is, let's say here. Let's say this is the line, tau x equals 0, which is k squared equals 2c2. So this line seems to be a dividing line, an important dividing line for the Bridgeline stability of the cotangent bundle. And what we mean by that is, if you have a minimal surface of general type that's about where the invariants are above this line, it seems to be much easier to force the rank of A to be at most 2, which means it's much easier to prove that the cotangent bundle is Bridgeline semi-stable for surfaces in this region. But then in the literature, it seems much harder to find examples of surfaces that are in this region. It seems much easier to find examples of surfaces that lie in this region. But then when it comes to stability theory, it seems much harder to prove that the cotangent bundle for these surfaces is Bridgeline semi-stable. Yeah, so we're particularly interested in examples of surfaces, minimal surfaces of general type that lie in this region, or at least below this line, but very close to this line. So here are some, a couple of results that we have. So let me just write down some concrete statements. Well, if we look at minimal surfaces of general type with geometric genus 0 and k squared equal to 9, and then these will be the fake projective planes. So the fake projective planes. And there are exactly 100 of these fake projective planes. And a good reference is a paper by Saiki Yang and Qingwei Lai. So suppose X is one of the 92 fake projective planes where the Narang-Savary group has an ample generator. Yeah, and after a conversation with Lai Qingwei recently, we think that maybe we can remove this condition on only 92 of these 100 planes. Maybe this statement works for all the fake projective planes. But let's say X is one of these 92 fake projective planes where the Narang-Savary group has an ample generator. Then we can show the cotangent bundle is Bridgeline stable. Yeah, when the parameter T is any positive number. Yeah, so if your ample class is any positive multiple of the canonical class, and you take the divisor B to be 0, we know the cotangent bundle is Bridgeline stable. Now, if you just take an arbitrary surface where the canonical class is ample, we can also show that, so here let X be any smooth projective surface where the canonical class is ample. And we assume that the cotangent bundle is non-split, so it's not strictly slope semi-stable. Then we know we can show there exists, and we can write down a formula. And there exists some T not bigger than 0, depending only on C2 and also k squared, such that if you take T to be bigger than this cutoff point, then the cotangent bundle is Bridgeline semi-stable. Yeah, but then what this number is depends on these particular invariants, of course. And if you want more concrete. So for any surface where the ample class is ample, we have a formula for this number. But if you want this number to be nice, and by nice we mean maybe it's less than or equal to 1, or it's 0, so that the cotangent bundle is always semi-stable, then you need to know a bit more about your surface. And so we have a wish list. So to obtain more explicit results, we found that it would be very helpful if our surface has the following properties. So right, we want the canonical class to be ample. And then, as I mentioned, it would be very helpful if this order pair C2 comma K squared is in this region, or at least below, but very close to this line. So we are hoping to find examples or more examples where 6/5 times C2 is less than or equal to K squared is less than or equal to 3C2. Yeah, so this is just the BMY inequality, and we found that this condition will make the destabilizing sequence of the cotangent bundle less complicated. And then in analyzing the destabilizing sequences, it's really hard to say concrete things without knowing the Narang-Savary group and the intersection numbers completely. So we are also hoping to find examples where we have a good description of the intersection numbers in the Narang-Savary group of the surface. Okay. So this is the end of what I want to say on K3 and surfaces of general type. And in the if there are no questions, I'll try to say something about final surfaces in the remaining time. Okay. So for final surfaces, well, the main difference is, right, we can no longer use multiples of the canonical class as our ample class in defining Bridgeline stability. So we have to use a scalar multiple of the NT-canonical class. So we use omega, which is T times the NT-canonical class. So I'll write it as minus TK. We use this ample class in defining Bridgeline stability conditions. So we often write the Bridgeline stabilities we use as sigma sub minus TK. And then for technical reasons, we will look at the tangent bundle instead of the cotangent bundle. Yeah, but the Bridgeline stability of the tangent bundle is equivalent to the Bridgeline stability of the cotangent bundle by a result of Christian-Martinez. And so let's focus on final surfaces that are blow-ups of P2. So I'll write X to denote P2 blown up at endpoints in general position. This is P2 blown up at endpoints in general position. So here, n would be by the classification of final surfaces, n has to be between 0 and 8. So we've computed such a cutoff point T node for some of the final surfaces. So we've computed T node for some of final surfaces Just to emphasize, so T naught means if T is bigger than T naught, then the tangent boundary would be bridge line semi-stable when the ample class is minus TK. So we have this table of the best T nodes that we have found. So let's say we make a table according to the self-intersection of the canonical class. So they go from 9 down to 1, 3 to 1. And then the number of points involved in the blow-up would be 9 minus k squared. We have 0, 1, then 6, 7, 8. So we can prove that when k squared equals 9 and 2 and 1, so k squared equals 9 is P2. We can show that T naught in these cases, we can take it to be 0. Meaning for these three surfaces, the tangent boundary is bridge line semi-stable for any positive T. Yeah. And then for the other surfaces, let me just focus on the case of k squared equals 3. So right now, the best bound we have is √3/2, which is roughly 0.866. So if T is bigger than this number, then we know the tangent boundary is bridge line semi-stable. And now, a while ago, we only had, the bound we had for this case was only 2. But we were able to bring it down to √3/2 because of a result by Jie Liu from 2018. So he had this proposition in his thesis, which says the following. So if X is a cubic surface in P3, or equivalently P2 blown up at 6 points, so which is X6 in our notation. And then if you take any subsheaf of the cotangent bundle that's saturated, meaning the co-kernel is torsion-free, and if you assume this subsheaf L is invertible, so it's a line bundle, then minus k times C1 of this line bundle is less than or equal to -3. So I mean, what does this result mean? Well, let's think about what we can say about this number if we didn't know Liu's result. So without Liu's result, this is what we can say. Well, so we would know that the tangent bundle at least is slope stable with respect to the anti-canonical class. So this means that the dual of the tangent bundle, namely the cotangent bundle, is also slope stable with respect to the anti-canonical class. And so from the definition of slope stability, if we compute the slope of this line bundle L, it has to be strictly less than the slope of the cotangent bundle. But the slope of the cotangent bundle is minus k times the C1 of the cotangent bundle, which is k, over the rank of the cotangent bundle, which is 2. So this is minus k squared over 2. Now we know k squared is 9 minus the number of points involved in the blow-up. So k squared is 9 minus 6. So this is -3/2. So the slope of this line bundle, that's a subsheaf of the cotangent bundle, is strictly less than -3/2. But a line bundle has rank 1. So its slope is just minus k times C1 of L over 1, so just minus K times CL. But then this number is an integer that's strictly less than minus 3 over 2, which means minus K times C1 of L is less than or equal to minus 2. Yeah, so Liu's result improves this upper bound from minus 2 to minus 3. And it allowed us to bring down this bound T naught from 2 to less than 1 in the case of K squared equals 3. Yeah, so the point of this example is it seems, and we have other results where it seems to us that if we knew much more about the explicit geometry of these Fano surfaces, then it seems that it would be much easier to prove the Bridgeline stability of the tangent bundle on Fano surfaces. Yeah, but none of us are experts in the geometry on Fano surfaces. Yeah, so hopefully this will get some in the audience interested, and hopefully this calculation also shows that if we really make use of the explicit geometry of Fano surfaces, then do something that you can really prove the Bridgeline stability of the tangent bundle, and that's a motivation for checking whether the theory of the form Hermitian-Mills equation, whether that corresponds or how it's related to the theory of Bridgeline stability conditions for high rank bundles. So I think I'll stop here.
Yeah, thank you very much. So is there any question from the audience?
What happened to the rest of the table? What happened to T naught between n equal to 1 to 5 to win?
Right. Right. So, I mean, we've actually computed these numbers as well. But the reason why I didn't write down the complete table, one reason was for K squared equals 8 and 7, when we try to compute T naught by hand, there were too many cases. So we ended up writing MATLAB codes to do the computations. Yeah, but we want to double check the codes. Yeah, but the numbers we have for the rest of the table, they are all less than 2. Yeah, and we are still in the process of trying to improve some of them.
Thank you. Any more questions?
Do you have similar results for other types of surfaces, or are you planning to do that?
Right. So let's see. So K3, we feel like right, the cotangent bundle is always Bridgeline stable for any ample class. So I should point out, in all these results we have, we always assume that the this parameter B in the definition of Bridgeline stability is 0. Yeah, so definitely you can try to see whether similar results or whether there are results on the stability of this tangent or cotangent bundle when B is non-zero. Yeah, and so as I mentioned, for general type surfaces, right, we have these results. We also looked at the case where the geometric genus is 0 and K squared equals 8. And then for Fano surfaces, we haven't looked at P1 times P1. One of the reasons is in this case, the tangent bundle is only strictly slope semi-stable. So you have to work a bit harder to see whether it's Bridgeline semi-stable when T is large.
Okay, but how about, say, like abelian surfaces? Does it make sense
Oh,
to
yeah, right. Of course, it also makes sense to look at these surfaces. And so in algebraic geometry, yeah, those are perfectly good questions to ask and try to work out. One reason we haven't thought about those surfaces is simply because on the equation side, people seem to be more interested in genotype and funnel. Yeah.
Okay, thank you.
Any more questions? So maybe a question. I think maybe you tried to explain, but I didn't understand. So at some point you were trying to find the T0 as close as possible to the wall.
Yes.
And what was the motivation for trying to find such a optimal T0?
Oh, right. So yeah, if you can work out where the actual wall is, then you would know that at this wall, say the cotangent bundle would be Bridgeland, strictly Bridgeland semi-stable. You will know above this wall, the cotangent bundle is Bridgeland semi-stable. And you will know a little bit below this wall, the cotangent bundle is not Bridgeland semi-stable. Yeah, and then if you work a bit harder, you can potentially show that everywhere below this wall, the cotangent bundle is not Bridgeland semi-stable. Yeah, so then it's as if within this one parameter family, you know everything about the Bridgeland stability of the cotangent bundle.
Right, I see. So I agree that it would be very nice to find the wall, right? But why? But it seems that you're saying the goal that you want something above the wall. So why don't you want to find T0 on the wall? Why don't you want to find the wall?
Yeah. So maybe I can phrase it this way. So right. So if you assume T is exactly on the wall, then you have such a show exact sequence, and you have this equation. Yeah. But then what happens is very often, yeah, because these equations involve the Chern characters of A and Q, and you don't always know exactly what the Chern characters are. So when you write down these equations, but you don't know the Chern characters of A and Q exactly, very often you only have maybe upper bounds for certain Chern characters. Yeah, so then it becomes as if you only have an upper bound for this wall instead of knowing exactly where it is.
I see.
Yeah.
Okay. Yeah. Thanks.
And so that's why results of Jie Liu's, yeah, where he gives us improvements on intersection numbers involving Chern classes. That's why these results become very helpful.
Right. Nice. Any other questions? No? Yeah, let's thank the speaker again. Thank you very much.
Thank you.
Yeah, I think it was a very nice talk. Also, the beginning was very informative, I think. Yeah, I liked it.
Thank you. Yeah.
Yeah, so thanks. Bye-bye.
Okay. Bye-bye.